Analytic solutions. Welcome to the show. These are the solutions to the time-independent Schrodinger equation for the harmonic oscillator that require the use of tools from differential equations, namely power series solutions. The algebraic method with the ladder operators was clever and fun. However, this is another tool that is used and will be seen again later in the book. We've seen polynomial solutions before in E and M, namely the Legendre polynomials. These two have a brand name, known as the Hermite polynomials, named after the French mathematician Charles Hermite. They too are orthogonal functions, sets of functions, just like we've seen before. So, for this problem, what we want to do is use the recursion formula, equation 2.85 in the third edition of Griffith's book, to work out the 5th degree Hermite polynomial and the 6th degree Hermite polynomial. Invoke the convention that the coefficient of the highest power of xi is 2n to fix the overall constant. The recursion relation is developed from the power series used to solve the time-independent Schrodinger equation for this potential through what's known as the method of Frobenius. This is unique insofar as it requires two parameters, the state n, which leads to the allowable states j based on the ability to normalize. Further, as we saw in the theorem earlier in the book, we knew that the solutions would be even or odd, so the polynomials will alternate between even and odd polynomials. That gets truncated at the level of n equals j, as we see in the recursion relation. Let's take a look. So when we have the level of n equals j, this top goes to 0, so it truncates all the coefficients thereafter, and we stop there. So since we want h of 5, the 5th level Hermite polynomial, we know that n equals 5, which is what we state here. Reading off this form, the allowable levels that are going to be obtained and that keep this odd are j equals 1, 3, and 5. And so here's how we calculate the coefficients in order to create the polynomial that we want. So for the first allowable level of j equals 1, if we plug in 1 to the level j here, we see that we get the coefficient on the third degree of the polynomial, so a sub 3. So by plugging in 1 to the fraction side of it, we get 1 here, 1 here, 1 here. Pretty easy there, and we have a coefficient of 1 there. Alright, cool, not too bad. We just simplify the fraction down, and we see that a sub 3 is equal to negative 4/3 a1. Now is where the stuff starts to get tricky as we move through the allowable levels. So if we plug in 3 for j, that gets us to a sub 5. No big deal. Figure what this is. Note that now we have a sub 3 here instead of a sub 1. So we find out what, after simplification, what the coefficient on a sub 3 is. But we know that we have what a sub 3 is in a formulaic expression, namely negative 4/3 a1, so we plug that in here. And what this allows us to do is simplify this down to where we only have one unknown coefficient, namely a1. And let's go see how we solve for this in the next page. Well, as promised, when n equals j, we get a truncation here. And we see that when we plug in j equals 5 right here, then it goes to the level of a7, and we see that we get a 0 up here in the numerator, so that goes to 0. Easy enough, that's where the truncation ends, and we move on. Okay, so we know that we go up to this 5th degree solely because of how we can normalize and what is a normalizable or physical solution. Cool, we like that, easy enough. Now what we need to do is form the polynomial. So note here that we have the n degree that is odd, so we need only odd powers. And that's what led to our allowable states of j. Cool, easy enough. So here we have a1 with the first power of xi, a3 with the third power, and a5 with the 5th power. Remember, a7 is truncated, so we're good. With that being said, we can plug in a1, a3, and a5 in terms of all a1s. And that was the benefit of doing it That way, where we could substitute in, now we can have just a1 factored out, which is what we do here. Cool, we like that. Let's also note here that we have this fraction here, which is divided by 15. Let's throw that out front so we have nothing but whole numbers on these exponents. And so we get a over 1, a to the 1 over 15. But we have to put a 15 here. We have to multiply by 15 or by 5 here, since we have a 3 in the denominator, and then that just gets factored out. Easy enough, pretty common tactic there. So after we're done with the factor method, the question still remains, what is the coefficient of a1? And this is where we use the convention of the highest coefficient takes on the value of 2n. Okay, so we restate what was given in the question here. So since our highest power is 𝛾 to the 5th, which we already knew that since we want it into the 5th, n equals 5 here, we know that 2 to the 5th has to be what we set the highest coefficient equal to, and that's 32. So what we say here is that we take this 4 over 15 a to the 1, which is the coefficient on 𝛾 to the 5th, and we set that equal to 32, which is what we see here. So let's solve for a1. And we see that this is 32 times 15 over 4, which is just multiplied by the reciprocal, easy enough. And we see that we get a factor of 8 times 15. We write this solely because we already factored out a 15, and it just makes it easier to sub in. So cancel, cancel. Now we just have to multiply all of these by 8 to fix the coefficients. And we see that we get the 5th degree Hermite polynomial. Not too bad, but boy is it messy to start this. This question wasn't assigned as one that was one that everybody should know by the authors. However, I disagree because of polynomial solutions. Plugging into these forms is highly important, and this is not going to be the last time we see this. So we'll go try the even case now and compare our result. Well, now that we have the odd case done, we can now calculate the even case, which the case here was h of 6 of 𝛾. So this tells us that we have n equals 6. So our allowable states are 0, 2, 4, and 6. And we're going to use the same method as last time. Push the j's in, simplify through. Then once we get the base case, substitute in the case before it to get it down to all a0's here. First case easy. Second case we get an a2. So we substitute in the case above it, which is negative 6 a0. Simplify it down, easy enough, 12 over 3, the two negatives cancel, good to go, good to go. So we end up with 4a0. One more level here, we get 6 minus 4, plug in 4 everywhere, so our level is 6, and we get negative 2 over 15 a to the 4th, so plug in the a to the 4th that we found just above it, which was 4a0, and we see that we get something times a0. Of course, here we hit the truncation level when n equals j, so that coefficient goes to 0, and now we're ready to determine what the unknown a0 is. Wonderful. So now that we have all the terms we need to up through the truncation term, we can now make our power series solution, or our polynomial solution rather. Here we see that we have a0, a2, a4, a6, and a8, which of course we know is a 0. So I'll just show you how that doesn't matter once we get there. That coefficient being 0 gets rid of all higher order terms. So now we just plug in a to the 6th in terms of a0, a to the 4th in terms of a0, and a2 in terms of a0. And now of course we do the factor out method like we did last time, doing the double factor of this fraction here and the a0's. And now we know that in order to calculate the leading coefficient, it needs to be equal to 2 to the n equals 6 in this case, is highlighted in the green. So what we do, 2 to the 6th, well, set them equal. Negative 8 over 15, right here, a0, equals 64. And so solving for 64, we multiply by the reciprocal, bring that negative sign with you. Yes, it does matter. And we see that 64 divided by 8 gives us that factor of 8 again. And so, just like last time, these 15s keep canceling. But we need to multiply the negative 8 into everything, and that's why we get the negative 120, 720, 480, and so on. Now when you graph all of these, you note that we have alternate between even and odd, which was one of the first proofs we did in this chapter, so that works out great. We also note that these fluctuate quite frequently with these coefficients, but that's all to make sure that things are normalized within the complete set of solutions. So we take the Hermite polynomial, multiply it in with some of the exponentials, and we see that the total level for that energy level is what gets normalized. So it all works out. Wonderful method, but boy, is it messy. So get your head wrapped around that. We'll see more series solutions soon. And as always, until next time, happy learning.